Hi, and welcome back to my videos for General Chemistry 1. In this video, I want to tell you about how we can find out how strong the bonds of a crystal are. Many crystals have especially strong bonds, including these beautiful crystals. In fact, they're the strongest bonds we'll see in this course. So, how do we measure them? Well, in the last video, we saw that we can use bond enthalpies to estimate the enthalpy of a reaction. As we said in that video, the enthalpy of the reaction is approximately equal to the enthalpies of the bonds we break minus the enthalpies of the new bonds we form. But all the bond enthalpies in this table are for covalent bonds, like the ones in a molecule of glucose. On the other hand, the bonds in crystals like these are all ionic bonds. So there must be a similar table of bond enthalpies for ionic bonds, right? Actually, there's not. It turns out that we can't calculate the bond enthalpy for an ionic bond the same way we do for covalent bonds. The reason has to do with the nature of the ionic bonds in a crystal. For example, the mineral halite is made of sodium chloride. The cubes you see here are large single crystals of sodium chloride. If we were to zoom in, we'd see that the crystal looks like this. The yellow atoms are the sodiums, and the orange ones are chlorines. The important thing to notice here is that, unlike a single NaCl molecule, each atom here is bonded to more than one other atom. In fact, each atom is bound to 6 others, to the left, right, front, back, top, and bottom. So there are a lot more bonds here than there would be in a single NaCl molecule. That means we can't find out the strength of a single ionic bond just by breaking down the crystal. Instead, what we're interested in is called the lattice energy. The lattice energy is the energy that's released when we form a solid crystal from its gas phase ions. For example, if we form a crystal of halite, which has the formula NaCl, the lattice energy is the reaction where we start with the gas phase ions, in this case sodium plus and chlorine minus, and combine them to form solid NaCl. It turns out that the lattice energy, which is symbolized by the symbol delta U, is 786 kilojoules per mole for this reaction. If you compare that to the bond enthalpies of covalent bonds we saw in the last video, you'll see that the lattice energy of NaCl is higher than all the bonds on this table except for the triple bonds. This is because ionic bonds are almost always much stronger than covalent bonds, because the electronegativity difference is much larger, so the atoms in an ionic bond are more strongly attracted to each other. If you look at the lattice energies of other crystals, you'll find that many of them are even higher than for sodium chloride. For example, fluorite is a crystal of calcium fluoride, CaF2, and it has a lattice energy of 2240 kilojoules per mole, almost 3 times higher than for sodium chloride. Meanwhile, quartz, which is silicon dioxide, has an even higher lattice energy of 12,535 kilojoules per mole, and corundum, which is aluminum oxide, has an even higher lattice energy of 16,230 kilojoules per mole. One of the people who developed this method of determining the strength of a crystal, and of the ionic bonds in it, was the German chemist Fritz Haber. Haber was interested in all kinds of problems in chemistry, but today he's remembered primarily for 3 things. First is the significance of lattice energy as a way to determine the strength of an ionic bond, which he developed with the help of his co-worker Max Born. The other 2 things that Haber did are even more interesting. One of them was a wonderful service to the world that helped feed thousands of people, and the other was a horrible invention that has made warfare even more terrible than it used to be. First, the good news. Haber invented a way to create ammonia by combining nitrogen from the air with hydrogen. The ammonia could then be used to manufacture fertilizer more cheaply than ever before, and in much greater amounts. This meant that thousands of poor farmers around the world could grow more food, and it was such a great benefit to humanity that Haber was awarded the Nobel Prize in Chemistry for his invention in 1918. Unfortunately, Haber also realized that ammonia gas is a deadly poison when inhaled, and when World War I broke out, he convinced the German military that ammonia gas and the equally deadly chlorine gas should be used to fight the enemy during the war. He worked with the chemical companies BASF and Bayer, which still exist today, to manufacture chemical warfare agents. Because those gases are more dense than air, they settled into the trenches on the battlefield, killing thousands of soldiers who were stationed there. Both chlorine and ammonia cause suffocation and great pain, and inhaling either of them is a terrible and frightening way to die. So Haber performed a great service to humanity by feeding many people through the fertilizer he helped make cheaper, but also caused suffering of a kind that's terrible to think about. It's always important to remember that science is only a way of studying the world and finding things out. What we do with our discoveries is what makes them good or bad. You'll talk much more about problems like these if you take a course in scientific ethics, which I hope you do sign up for someday. These are important issues to think about, and we're all better scientists when we're aware of the way our work can affect other people. Well, that's all for now. When we meet again, we'll start looking at the shapes of molecules. Unlike the Lewis structures we've been using, molecules usually aren't flat. Instead, they can take on lots of interesting and beautiful shapes, which we'll talk about soon. So, until next time, have a good week.